Thank you for joining us. For those of you trickling in, there's more chairs down below, so feel free to come on down. I'm pleased to introduce our next speaker, Jules Damji from Databricks. Jules is an Apache Spark developer and a community advocate with Databricks. Prior to Databricks, he worked as a developer advocate at Hortonworks. He has extensive software engineering experience, having worked at Sun Microsystems, Netscape, VeriSign, At Home, LoudCloud, Opsware, and ProQuest for over 20 years. He's presenting a talk titled A Tale of Three Deep Learning Frameworks, TensorFlow, Keras, and a Deep Learning Pipelines. Please join me in welcoming Jules.
Thank you, guys. Thanks a lot for coming. Good evening or good afternoon, however you actually want to say that. I was a little worried about this was the last session or a second to the last session, and I had invited a lot of my imaginary friends to fill up the slots. But it's really nice to see all of you here. Thank you all for coming. As Arti said, my name is Jules Damji. I'm the Spark developer advocate at Hortonworks. We were supposed to co-join this with my esteemed colleague, Brooke, who is a data scientist at Databricks. She's unfortunately couldn't make it because of some family obligations. So you're stuck with me, boring Jules, for another 40 minutes or so. So I'll try to go through this fast. This is what I'm going to talk about today. This is the agenda. What has big data done to us? You know, the impact of big data. We are actually living in the zeitgeist of data. Data is everywhere. It's permeated our lives. What's the impact? What is it actually doing to us? And why, at this particular point, Apache Spark has become the de facto data processing engine, along with the ability to support some of the deep learning pipelines frameworks that I'm going to talk about. We'll do a short survey of 3 deep learning famous pipelines that have sort of emerged over a period of time. And then I'll give a demo if my Wi-Fi works. I've had a lot of problems this morning with it, so maybe I'll have a chance to be able to show you something, how you can actually do deep learning on Databricks and using Apache Spark. And then finally, hopefully, you have questions for my prepared answers. So what has big data done to us? If you actually look at the way the data has evolved over time, it's actually permeated our lives. There are countless machine learning applications, there are countless machine learning programs that we interact with daily, whether we like it or not. Some of us, depending on what side of the fence you are, it has permeated our lives. It sort of shattered our confidence in is AI coming to the point where it'll actually take over humanity? And it started with this fear of deep learning taking over by playing and beating Sidol. If you actually played Go, it's one of the most complicated games, and nobody actually thought ever that a program would be able to play this very intuitive game by learning itself. And today we interact with Netflix and Amazons and Shopify and Spotify and Zappos, and they tell us exactly what kind of shoes we like. We go to dress and we wonder how this is actually happening. And there is a lot of algorithms behind it, there's a lot of data. So these are the things which are actually happening. And drug discovery is another place where the machine learning is actually being used quite a bit. Postal code was something that actually started quite early on, where they were recognizing handwriting from very early on before we even thought about number plate recognition. We see prediction models using machine learning algorithms in the financial industry as well. And we all have interacted with Siri, and we all have interacted with Alexa, where the natural language processing has taken a tremendous leap forward in how they actually process those things. And obviously, needless to say, what the transportation industry has actually leaped forward in terms of how it uses automotive self-driving cars by using the object detection, by using image classification. And there's a large system behind it that actually does all that in real time. And face recognition, those of you who get mesmerized by walking into a mall and somebody actually recognizes your face and pops out, what are some of the things that you actually may like? So these are the things that actually have permeated our lives. But what's hard about it, right? We see that, interact every day, we play with it every day. What's hard about it? See, the hard part about AI really isn't AI, it's the data. And this was a paper that was actually published in 2015 by Google. And they claimed that the machine learning code that surrounded this large system of very complicated prediction models was that little green box. You see that? That's the amount of machine code that actually runs, but it needs in proportion to all the other boxes that you actually had. You need infrastructure to do processing, you need infrastructure to do programming, you need infrastructure to do serving, you need infrastructure to do all the configuration and feature attraction. All these surrounding entities that need to be done in a cohesive and in a really collaborative manner is the difficult part of AI. And that's where Apache Spark comes into play, because it has the ability to give you this unified way to handle all the external things that you actually need in order for your machine learning code to actually work in a manner that you actually expect in terms of prediction. And that's what we call the 99.1% problem, where the 99% of the problem is not so much the algorithms itself, because the algorithms are efficient. It's the data that actually needs for it to be fed, and the data has to go through all this, and all these other proportional boxes are the ones that actually give you the ecosystem, the infrastructure to actually do that. So you may ask why Spark is actually a de facto engine, because it was actually developed with that particular idea in mind to actually unify all these different workloads. And it is one of the unified engines today that allows you to be able to actually do both data processing at scale, data provisioning at scale, and machine learning libraries that it actually now has met its first-class citizens. If you actually see on the left-hand side, everything is good for data, but it's not good for AI. If you see something on the right-hand side, everything is good for data, good for AI, because you got all these libraries, you got all these frameworks, you got all these algorithms which are actually part of the library, but the data is not there. But when they actually work together, you actually get that particular program. You bridge the build by having a unified engine. And one of the things that we have actually done at Databricks is the ability for us to actually bring all these disparate workloads together under one particular platform, which if you look at the center, it's actually Apache Spark, and you got all these frameworks on the right, and you got very highly optimized Databricks Delta that actually ingest data. And up at the top, you have all these workbook notebooks that allow you to actually work and be run both on Azure as well as on AWS. But that's not what you came here for. You actually came here to find out, if I was a machine learning developer, how do I get started? What are some of the things that I should consider if I'm going to start writing deep learning applications? What are the things? And that's what I really want to talk about today, is this particular survey of deep learning frameworks, because we are actually entering an era where having a knowledge of machine learning and data science is going to be as imperative as being able to actually do arithmetic and algebra. It's just a matter of time. And so if you're getting started, how do you actually get started? There is a zoo, literally a zoo, metaphorically speaking, of all these frameworks that exist, right? There are all these languages. What language do you choose? It depends on how comfortable you are, whether you use Python, whether you use C++, whether you use Julia. But today I'm going to emphasize on 3 of these particular frameworks, because I'll give you my justification. I'll make a case for each of those and why these sort of have emerged over the period of time. And I'll talk about that. So let's first go straight into the first one, TensorFlow. What is TensorFlow? You probably get, how many of you actually heard of TensorFlow? It's like asking, have you heard of Trump? You all have, thank you. Right, in different contexts though. One is popular in a different sense. But open source, Google started this particular framework in 2015, and current version is 1.10. But it was built with true proposition in mind at Google, right, in 2015. The guys, James Dean and his incredible team and people at Google Brain said, we want a default framework to do all our AI, all our deep learning applications, all our machine learning applications. And the true propositions were that the framework has to actually be able to be very mathematically intensive, so we can express mathematical computation, because inherent in machine learning algorithms are all these mathematical functions that they wanted to embrace as part of the language as low-level operators, so they could express those in numerical way. And the second proposition was that it has to be low level, so I can write very primitive operators, and I have to be able to run it on different architectures at any time that I can use it. So it doesn't only have to be on CPU. I should be able to run it on GPU. I should be able to run on TPU and FPU, or whatever the next generation architecture was. And because of those two requirements, it was actually written in C++, so it's actually close to the metal. So you can actually run it quite efficiently in a distributed manner, and you're very close to it. But the interesting part about TensorFlow is not so much the fact that it's written in C++. The important fact was that in the distributing world today, there's a new paradigm in how you actually execute things, how you express your computation. And data flow graphs is one of the way how a lot of people in the academic world and now mainly in industry actually express large mathematical computation that can actually be distributed. If you look at Spark, how many of you use Spark? Right? Spark has this notion called directed accelerated graph. You express your query, you actually create a DAG, and the DAG is a bunch of nodes, and the edges are how they're actually connected, and they get executed lazily. In other words, that you express your mathematical computation, and you give that DAG out to your cluster, and it executes in parallel. And that's how they express the computation. And they realize that because of the fact that I can express something in a directed accelerated graph, I can optimize what are the things that I actually want that they have to be executed in parallel, or what are the things that I want they have to be executed in sequential. And that allows them to express the computation in that way. But you don't have to worry about it. The underlying engine does that. And that's what TensorFlow actually wanted to do that. So you can think of nodes as units of computation, mathematical units of computation. It could be multiplication of matrix. It could be joining two arrays of large computations together. And the nodes in TensorFlow nomenclature are tensors. That's where the name tensors comes from. And tensors are nothing but vectors of different dimensions. You can have a tensor of a scalar of dimension 1, or you can have a vector of dimension 2, or you can have a matrix of dimension 2, and so on and so forth. And that's where the name TensorFlow comes in, because they wanted to do a mathematical computation that could actually use these vectors. They could represent anything in integers or float, and then do highly complex computation that way. The other idea was lazy execution that allowed them to be able to actually execute lazily, which means that I only execute when I created a session and I tell it to execute. Now in 2.1.7, they had this notion of eager execution. And eager execution is those of you who are actually familiar with procedural language programming. Most of us are that's how we actually program. We write a procedural language and we go step by step. And this allows you to configure TensorFlow so that when he actually runs it graph, it actually does it in a sequential manner, which is what we think about in a very sequential manner, as opposed to doing it in a functional manner, which is what this distributed computing is all about. Now, just to give you a flavor of TensorFlow code, let me just, can you guys see it? All right, brilliant. In TensorFlow language, they have this notions called placeholders, variables, constants, and sessions. And these are, you can think of these are the primitive operations that you can actually use in TensorFlow. It's very low level, and you'll get the flavor of why it is such a low level language. So what I'm doing over here is I'm trying to create two variables called A and B, which are going to be used to do my linear equation. And then I create a metric multiplication. I say A is matrix A and B is matrix B. Compute that and give me the result using TF math mul, which is an operation to do matrix multiplication. And in deep learning, especially in image classification, there's a lot of linear algebra, there's a lot of matrix computation, a lot of linear dot matrices going on. So they want to have the ability to actually do that. And then you actually create a session with the cluster, and you actually run that particularly to get the result. Fairly low level, right? It is like writing C program. You're telling exactly how to do something. And that's actually what they wanted to do that. But over a period of a couple of years, they begin to realize that people will come from different parts of computer background. Some might be very high level, so they actually needed high level APIs to be able to actually sort of encourage and build the community, such as yours who are here to understand what it is all about TensorFlow. Here is a hello world of deep learning application that you will probably invariably, if you go to TensorFlow tutorial, you will use how to classify images of 10 digits called MNIST, which was a data set And here too, you can see it's a very low level. I'm not expecting you to actually understand this particular code, but I'm just giving you a flavor so that you actually know what TensorFlow is all about and what you're actually dealing with and what you actually know. So they have this built-in parameters that allows you to input your data. You can actually create placeholders for it. And then you define your linear model. Y is equal to x plus y, and I'm going to use my model. Here's my weights, and here's my x, and I'm going to do a dot matrix. I'm going to have a bias added to it. I'll create my loss function, and I'll use my gradient descent to do that. And then I'll create my session, and I'll go ahead and execute that. Fairly low level, would you agree with me? Right? How many of you actually understood this particular code? It is fairly low level. Even if you actually have a strong machine learning background, you still have to understand and know exactly what you're doing, right? It's a fairly low level. Now, the reason, as I said, it was low level because the proposition was built on that. We actually wanted to have control over the deep learning and ML application that we run. And the reason why this sort of has changed over a couple of years for the good is you can actually see there is a programming stack that goes from low level all the way up to the top. So it was built with the ability to actually write very low level functions that we can actually distribute using flow graphs. And I can run on any of these architectures. I've seen TensorFlow applications run on Raspberry. Anybody got a Raspberry at home? Brilliant, try that tonight. All right, there is a notebook that you can actually literally run on it. You'll see the lights going crazy. But you can actually run on it. And then as you go up the stack, right, things become easier. As you get older, things become easier too. So there's Python API, which is a very popular API. There's C++, Java, Go. Swift was recently. You can actually do TensorFlow application in JavaScript. Anybody web developers over here? Anybody using JavaScript? Don't be ashamed. Denial is complacency, if you guys didn't know that. And then as you go up the stack, there's this pre-built layers and data sets and matrix that you can actually use. And then Keras. Keras is now part of TensorFlow, where you can actually create TensorFlow models. And I'll talk about Keras momentarily. And then there are CAN estimators that you can actually use, such as logistic regression, such as decision tree, and so forth. So depending on level of comfort, you can come in from any part of where you actually feel more comfortable. And that's one of the attractive features of that. So why would I use TensorFlow? I think as a developer advocate, I look for three things. When I'm looking at a platform, when I'm looking at a language, or when I'm looking at any particular new technology, there are three things I ask myself. One is there an open source community? Right? Is there an open source community that I feel comfortable interacting with, that I can actually go out and talk to, that I can attend meetups, that I can go to the conferences, that I can talk to someone online? Second, the APIs. How easy, how intuitive are the APIs? Is there loads of documentation? Are there loads of code examples? Can I, midnight, all of a sudden, after I had loads of coffee, inspired by writing something, all of a sudden I come across an exception? How many of you have come across a Java exception, or a Python exception, or a C++ exception in an API, and you literally cut and paste and put it on Stack Overflow? How many of you have done that? Come on, raise more hands. How many of you have done it? Right, you have done it, I know. And within minutes, some gal or some guy will respond. Right? Not out of his ego, but he will respond, or he or she will respond because they really want to actually help you. And I think this is where the community helps. Look at Big Data LA. Look at all the yellow shirts today. These are the people who are actually making things happen. It's the community. Huge community of TensorFlow, huge documentation, loads of stuff, right? So those are the three things you as a developer would look for. And I think that really determines the success of a platform, is the community, loads of documentation, loads of contributors, and feeling of psychological security where I can pop something out on the internet and somebody will give me a good answer. And somebody will give me a better answer, not because one answer is better than the other one, but you learn something. So you can actually learn and share because of that. And I think TensorFlow actually has done that over a period of 3 or 4 years, and has actually emerged as the de facto platform to actually use a lot of deep learning applications. So those are the three things. The other thing cool about this is that, how many of you actually have written multi-threaded programs in your life? Right? Is it easy to debug? right? It's one thing to actually write a threaded program on one CPU and then step through the debugger and try to repeat it. It's another thing when you actually have multiple cores, and all of a sudden now you actually have different kinds of race conditions. It gets even more complex when you actually have a data flow that's actually running across a cluster. How do you debug that thing? How do you actually figure out what your program is doing? And I think one of the things that TensorBoard allows you to do is take your flow graph that you actually have written and show you how your tensors are coming in, how they're being manipulated, how they're being executed, and then go out the other way, right? And this is something that is probably the most enlightening thing I actually have seen. If you are writing TensorFlow applications and you have this really complex application that you're trying to debug, TensorBoard is a good way to visualize your unit of execution within a node within a DAG. And you can enable eager execution to actually see each and individual nodes. The other bit, today, if you're a data scientist, one of the things you normally do in your iteration, you create a particular model, you version a model, you test it, you validate it, and you're happy with the results, with the prediction. You've got a good 90% or 95% accuracy, depending on your tolerance. You put it out on production. But then something changes, and you got to have another version, and so on and so forth. So the TensorFlow serving has the ability to actually version models and then deploy it to your production site on any of the architectures that I actually showed you. Right? So those are all the good things. So Jules, you have told me all the good things. What are the bad things? So what, right? I mean, what's the big deal? Yes, there is a steep learning curve, but it's very powerful, right? It is very powerful because it actually gives you control. And if you're a control freak, then most developers are, this is actually good. It's a low-level API, right? And because of the low-level API, you are pretty much in control. It's like those of you who made a switch from Spark RDDs to data frames, you actually saw the difference, right? The RDDs told you how to do something. The data frames actually told you what you wanted to do that. It was more declarative way. So this is a very low level. Now it presumes that you know a lot of machine learning. Nothing wrong with that. Bloody learn it, right? Because we are actually in an era where I think the initial concepts, you don't have to know the mathematical computations behind, but you have to understand the fundamental concepts. What does it actually mean when I'm actually doing a gradient boost? What am I doing when I'm looking at the loss? What does it actually mean to have a high accuracy? What does it mean to do hyperparameter tuning? You don't have to understand the math behind it, but you actually understand conceptually what it actually means, right? So learn it. Now here is the interesting part. Here is the consolation, which is that even though the fact that TensorFlow is a very low-level programming language and a framework popular among data scientists and people who have PhDs, but you don't have to have a PhD, there is a consolation. There is another high-level estimator API called Keras, which is now actually part of that. And incredible integration with Keras. So you don't actually have to know Keras. I mean, don't have to know TensorFlow. You can actually just use Keras, which gets translated into TensorFlow graphs to do your execution. So TensorFlow is the next thing I want to talk about. What is Keras? It is not the Greek mythology, two evil sisters that actually destroyed their kingdom. Keras over here is the horn, which actually gives you the enlightenment or the sound of enlightenment. That's what Keras actually means. And what is it? Right? What is Keras? Again, like TensorFlow, it is an open source Python library with APIs for deep learning. It's currently 2.2, written by François Chollet, who's a French computer scientist, now works for Google. Makes sense. So that's why they've sort of made it part of the first-class citizen. And it is a spec, right? It is like a Java spec. When Java was released in 1.2, it was a Java spec. And then Sun was the first one to release the JVM written to the spec. And then other people actually started writing JVM. So you can actually have your backend JVM running on Windows, running on Linux, running on Sun Solaris. Very similar. You can actually have a Keras API. And then the backend engine could be anything. Could be TensorFlow, could be CNTK, could be Theano. But here's the interesting part, right? The most beautiful part about that is that it's a high-level declarative API. You really don't have to sort of understand the low-level nuances. You can actually do it at a high level. It is more of what is it that I actually want to do, not how I actually want to do that. And that really gets people excited because it's a very declarative API to say, this is what I want to do. And it's great for building layers, especially when you're building neural networks, and has the ability to do very fast experimentation because of the fact that it's very modular. I can just create a bunch of neural networks together, connect them, and then just run my image classifier to see what my accuracy is, and so on and so forth. And it has a programming stack just like a TensorFlow. High-level API, you got the Python version of it, and you can actually have, by default, if you run on Google, you actually have Keras and TensorFlow. If you run on Databricks, same thing. Then they get the Tiano, there are all these other implementations. And if you're running a TensorFlow on other, you can actually deploy it on any of the networks. Why? Why would I want to use Keras? And I think in my case, my argument would be no different from what I made the case with TensorFlow. It has a popular, broader community. And if you actually look at what's actually happened over the period of years, if you see the number of people who are actually looking and making searches with TensorFlow and Keras, you can see Keras is really way up there. So those are sort of the two languages which are actually quite popular in the community. And it's very easy for you to actually build a small network to do your machine learning or to your deep learning applications by using what they call sequential layers. Now, just to give you a flavor of what the hello world that you saw in TensorFlow looks like that in Keras, you have an idea what I actually mean by how to do something as opposed to what to do something, right? And you'll notice that there is a pattern. There is a pattern in which how you actually write Keras application, and you define a particular network, right? You compile that particular network model, you fit the network, by mean training, you evaluate your network with your validation data, and then you predict that particular model with new data. So it's very simple. Here I'm actually importing some built-in functions to get my data in. I'm preparing the data so that I convert them into tensors, so it allows me to be able to compute that. Then I'm going to define my network. And all I'm doing over here is I'm defining my network to actually have a sequential layer with 2 dense layers and 1 hidden layer. And I'm going to have 512 neurons or 500 units of my pixels go in. And my last layer is going to be called dense layer that will have 10 units coming out. Why 10? Because I'm doing MNIST, and MNIST has 10 digits, and I won't have the ability to use a softmax function, which is a probability function that actually takes 10 units and gives you a number between 0 and 1. So the higher you are closer to that particular number, it will actually tell you whether this is a 9 or 5 or 6 or 7 or things of that sort, right? Then I tell the network to go ahead and compile this, and compile is I'm using a function. I didn't have to write the function. I just tell it, here's a function I want you to use. How do I know that? I Google it. No, I'm just kidding. You have to know a little bit about what is an Ardenstrop or what is binary trust and PB or what is an MSE. You have to have some knowledge of it, but you really don't have to write the function because they have been written for you and they've already been part of the package. So you just declaratively tell, this is a loss function I want to use, this is what I actually want to use. And then you fit with images that you actually have, that you have just downloaded it, and then you do a network prediction and evaluate. Now you can actually see, how many lines of code is that? 20? 15? But it's very declarative. I know exactly what I'm doing. I'm telling it what to do rather than how to do it, and then it will do the things for its own. So we saw sort of 2 frameworks right now. One is a very low level, gives you lots of control, expects that you know a lot of stuff about data science and machine learning. The other one is high level, doesn't expect you to know a lot, but a little bit, whereby you can actually build a fairly sophisticated application as time goes by, as you actually get familiar with it. And it's all written in Python, so if you're familiar with Python, it's actually a great language to do that. Which now brings me to the third and the final API called deep learning pipelines and transfer learning. And what do I mean by transfer learning? How many of you do transfer learning here? I'm going to ask that question again. How many of you do transfer learning here? I think you should all raise your hands. I'll tell you why. Right? Transfer learning is something that you actually have become an expert in something, or you have acquired a knowledge of something, and you're taking that particular knowledge and you're transferring something else, which is in the same domain. So, using an analogy, let's say you are a baseball player, right? You train yourself over a period of years to play baseball. It wouldn't be that difficult for you to take that particular way, your muscular memory, your ability to actually look at the board and play a sport, something very similar like tennis, right? It is about swinging the bat. It's about motion. Your transfer learning, you're taking your muscle memory and applying it to the same motion, right? Or whether you're playing cricket if you're from some part of the world. So that's what I actually expect everybody to raise their hand. But in the context of deep learning, transfer learning is the ability to actually take a model that has actually been trained before in one particular domain and then use the same model to train something else and predict that. Because rarely people actually build models from scratch because it takes a lot of resources, it takes a lot of time, it takes a lot of expertise. And so a lot of people, what they do is actually use transfer learning, that they've built the particular model, they've trained the model in one particular domain, and they're going to use that for something else. And this is very popular in image classification. You'll see people not writing models from scratch. Instead, they will actually use a trained model. What do I mean by that? So here's a trained model from ImageNet. Anybody heard about ImageNet? So ImageNet was a competition done about a few years ago where they actually took about, I think, 100,000 images, and they classified those images, they trained models to classify them into about 100 categories. So if I take that particular model and I give a panda, it's going to classify whether it's what kind of panda it is, and it'll give you the top 10 categories. And depending on where you are in your probability, you will actually have a fairly good accuracy of this particular. This is a panda, or it's a Jules dog in the backyard. Right, and so the idea behind a trained model is that you feed in the image, and then it uses all these particular filters to detect the edges and the curves and the lines and the circles as it actually goes down the deep hidden layers. And when it actually comes to the last layer, it has actually figured out that this is actually a particular face, or this is a leg, or this is part of my abdomen, or this is part of my chest. And then I'll give, comparing with the image that I have that says, oh, this is actually a panda, right? And I'll classify that using my softmax, which gives you the probability between 0 and 1. So if I wanted to take this particular image model that I've used for transfer learning and I put it into, and I wanted to classify a cat or a dog, how do I do that? I don't train the entire model again because that was going to take me years. I mean, months or weeks or however, depending on my computing research. I take the existing model that I have from ImageNet, and I'll put my input as a dog, and I'll take my last layer, which was a softmax, and I'll put my own image classifier to detect that as a dog, and then I'll substitute my softmax with a binary classifier that gives me the probability whether this is a dog, or this is a cat, or this is some alien being that I don't recognize. But that's a binary classification. And that's what I mean by transfer learning, which is taking an existing model because it's the same domain. Now, you can't use that with text analysis because these models have been trained for image analysis, right? And when to use transfer learning? You want to use transfer learning depending on these particular 4 conditions. You want to use when the data set is small and similar. When you want to use when the data set is very different, then you might want to do some fine tuning. And I'm going to run through this because I'm running out of time because I really want to go with the demo. And there's the third thing that I actually talked about is deep learning pipelines, which is actually part of the Databricks open source. We just released it as 1.0. It runs on Apache Spark 2.3. It's all in Python right now. Very easy integration, especially if you are using Apache Spark MLlib because it actually uses the same notion of data frames and pipeline. And it works with TensorFlow and Keras, so you don't have to install anything. It just comes with that particular runtime again. And you can actually write UDFs in Scala, so you actually build a particular model. You can give your data analyst to image to classify a particular image, and they can actually use that SQL. And it gives you the ability to actually distribute the hyperparameter in tuning, right? TensorFlow today, if you're running on most platforms, will do all the training on one machine, unless you run it on Google Cloud or somewhere else, where they actually take care of distributed learning. And it's very good for easy and transfer learning, which now actually brings us to the demo. So given the fact that I have been running into a lot of Wi-Fi, I'm not going to go through that. I ran this particular demo a few minutes ago. I had to go somewhere where there was a very strong Wi-Fi, so you can actually see it was just ran about 3 hours. So what I'm doing over here is I'm taking a VG16 model that actually has been trained from ImageNet, And when I talk about network, I'm talking about how many hidden layers I actually have, or what my input and what my output is. So I'm using a particular VGNet over here. And what I'm going to do is from Keras, import that particular, we'll import the particular libraries. And I'm writing a little function called predict images. So given a particular image, I'm going to first convert my image and put it into, reshape my image into tensor using NumPy arrays. And then I'm convert that particular image. I'll process that input. I'll predict. Right? I'll just predict the model because the model has already been trained and it has a function called predict. Right? So that's my overall function that actually does that. So what we're going to do, let's try to classify some African and Indian elephants, and let's see if we can actually fool the classifier. Hopefully we can. So I've got a few African elephants and one Indian elephant. Anybody know the difference between an African and Indian elephant? One has got large ears like mine, the other one has got very small ears. And so I've got a bunch of images over here. I load those images and I call my function called predict. And look what we actually got. So those are the 5 predictions that I actually get. So the first one was 73% probability. Now these are confidence level, right? Gave me a 73% that this is an African elephant. It is, because if you look at the ears. Then it actually thought that this was Tusker, which is a kind of an African elephant with 25%, and then Indian elephant down the road. When I took this one over here, it predicted that this is the Tusker, rightfully so, but also predicted it was an African elephant, and then it said Indian elephant. And then I actually fooled it by providing an ox to see if it actually figures out what it is, right? And it says, oh, it's a bison. No, it says ox. Right, the second one is ox with a lower probability, and then the third one over here, it thought that it was because there's a subtle difference between the two. They're actually pretty much the same. Right, one is an Indian elephant; it's got shrunk ears. It predicted that this was a Tusker, but then it said, "Nah, I don't think so. It's actually an Indian." Right now, here's an interesting bit. Look at this one. This is definitely an Indian elephant. This is not an African elephant disguised as an Indian elephant. This is the bloody Indian elephant, right? And I tried to fool it, and it says it's a bloody Pancho. Right? But then it inferred, hey, it's an Indian elephant. How does it do that? Well, it figured out I got all these adornments which are only used in India, right? Because of how they dress the elephants, and it says it's a bloody Indian elephant. Not bad. All right? Then this was inspired by Silicon Valley's Jin Yang, right? So I said, well, let's try to throw some food at the image classifier and see if we can fool it. So I put a cheeseburger followed by a hot burger and then his incredible handsome face. And the first image, it predicted with 98% predictability, it's a cheeseburger. And then hot dog, bloody hell, it better be a hot dog. That's Jin Yang's, right? It predicted hot dogs over here too. And then I tried to say, well, can I actually dress a hot dog and then see if I can, does it actually mistake that as a hot dog? And guess what? It said it's a bloody red bone. Not bad, eh? And then obviously I said, well, let's put some Jin Yang's picture over here. Now, notably, the image classifier doesn't classify persons, but what it tries to do is detect prominent fixtures in the image. So over here it says sunglasses, right? Not bad, with 44% predictability, and so on and so forth, right? So let's do something else now. What we did over here was we did all the prediction and all the inferencing on my driver. But what about if I actually want to distribute across a Spark cluster, right? And this is what I actually do. So I have a bunch of images. I use my deep predictor, and then I classify the images. And let's see what Jules comes up with. Jules came up with the description of wearing a suit. Do I look like I'm wearing a suit? No, I don't think so. Bulletproof vest. How about that? Do I look like a person who's got military tendencies? I'm not Trump. And then look at Matei, chainmail. Well, I mean, look at the uniform. He's got all these things that the knights wear when they actually brush against the other knight across from the horse. Now I'm going to change the model over here and then use inception to do the same thing. And I'll get different programs. Inception is the most new model that actually has one. Now, I think we're running out of time. There's a second part to this particular demo. There's a notebook attached to this slide, so when you actually go at home, you can actually do that. And what I've done here with the deep learning pipeline is I have taken my deep image classifier. I've took that particular thing out, and I've substituted that with it. And I classify cats and dogs, right? So that's my image, and I think we have a couple of more minutes, and let me just wrap it up, if that's okay. Going back to my slides. And so I think the takeaway over here is that of all these three particular frameworks, TensorFlow and Keras definitely are the winners. They are the default deep learning and machine learning frameworks that people actually use. What language should I use? Python is definitely the choice, right? Because an emerging new language called PyTorch, which is actually coming up, which is written in Python as well. And even The Economist had to chime in to say, you know, Python is the new language that actually it's going to make a difference in the world. And they say that by showing us, you know, how popular searches are on Python. And I would say, you know, given the fact that I work with a lot of data scientists, you know, Python is the default language for machine learning. And given the fact that three of the programming frameworks have Python APIs, so it's actually a default choice. So bubbles of takeaways, you know, which one should I use? I think if you want control, if you want low-level modeling, if you want to use deep learning, use TensorFlow. Nothing wrong with that. Use it, embrace it, learn it, and go with it. Flow with it, if you will. Keras is a high-level API. It's a declarative API. It allows you to do what you want to do something. So if you're actually new with machine learning, you know, I would urge that you start with Keras because it gives you high-level conceptual APIs you can actually start playing around with in a very fast, iterative manner, rather than getting intimidated by, I have to know this, I have to know that, and so on and so forth. So Keras is definitely what I would suggest. And then if you are coming from the Apache Spark background, and if you're using Databricks, and if you're using machine learning, MLlib, deep learning pipelines, and you want to do a lot of transfer learning, definitely deep learning pipeline is the choice. A couple of sources over here. I highly recommend this book by François Chollet called Deep Learning Programming. These are some of the resources. You will have it at your disposal. You can learn them, pick them up at any time. And here's my contact information. Feel free to send abusive email to me if you want. And my colleague is not here today, but we're going to be giving a similar talk in London called Tale of Three APIs, except instead of deep learning, we'll have PyTorch. So if you're in London, if you want to come to the Spark Summit, lots of good pubs, do join us. Thank you.